So our next speaker will be Francesco, who is originally a telecommunications engineer and fascinated by the Fourier transform, which taught him if you look at data differently, it will give you a different picture of the data. And yeah, he's currently working as a data scientist. And yeah, I'm looking forward to hear about how to evaluate marketing campaigns, especially online marketing, that you don't waste your money on Google ads, on your product names that will just give you a lot of clicks, but just steal the regular clicks you would get anyways. Right, thank you.
Thank you for the introduction. I'm Francesco, good morning, and I'm a data scientist. I'm currently working at Agile Lab, and we are a consulting company. We are based in Italy. And for one of our projects, we worked with a huge bank in Italy, and they asked us to develop a particular machine learning approach to increment, to optimize a process in their marketing campaign. So today we are talking about advertising, marketing campaigns. But when we looked at the requirement for this project, we realized that what they really needed was a causal machine learning approach, and not just a traditional one, but obviously they didn't know it. And so today I want to share with you some tips about causality and why causality matters and how and when you should consider causal approaches instead of traditional ones. And we will see a couple of examples in marketing use cases. The first one is how to estimate the effect of marketing campaign using causal inference. And then we will see how these techniques can be used to target the right customers in your campaigns. So let's start. Why does causality matter? Causality matters when you have to make decisions, and in particular, decisions about relying on data. And consider this. Here, suppose you are working in marketing and you're wondering if you should or not send your newsletter to more customers. And you may have some data and you notice a positive correlation between people who read your newsletter and people who buy more. But obviously, we all know that correlation does not imply causation, and this is our first pitfall here. Indeed, both newsletter reading and purchasing can be driven by a third factor, like user interest in our products. But we could have also a second pitfall here. We have a second pitfall here, and it's about intervention. Looking just at data, it's not enough, because here we are asking if we should or not send a campaign, a newsletter. And when you have this kind of questions, you are trying to solve a prescriptive problem. And I think that causality matters when you have to make decisions that require also your intervention on data and not just your observation, because causality can help you in understanding how data would change with or without your intervention. But let's see at our use cases for today. The first one is effect estimation. And here we have a question like, did my anti-churn marketing promotion have a positive impact on my customers? And suppose, again, you are a data scientist working in marketing, for example, for a huge bank, and your company realized a promotion with some budget, and now you want to estimate the effect on the churn. So you are trying to increase customer retention, to prevent churn. And you collect your data from this campaign and you get something like that. Here we have 1,000 people contacted by the campaign, 1,000 people not contacted, and we are looking at churn rates. And you can see that the churn rate among contacted is higher, so it seems that the campaign is not working. But obviously, we are good data scientists. We go further with our analysis, and we try to split this data by groups. So, for example, we could have a variable in our dataset, for example, churn risk. And now we are looking at this data grouped by two different levels of churn risk, low risk and high risk, and comparing, for example, just high-risk customers contacted or not, you can see that now our campaign seems really effective, and also for low-risk customers. This is called Simpson paradox, and basically we have a trend in our data, looking at global statistics, but when we group this data by for example, low risk and high risk, we get an opposite trend. So looking just at Bart Simpson is changing the effect that you are trying to estimate. And this is due to a particular form of bias that is called confounding bias. This is a causal graph. We will see other causal graph in this presentation. And basically, we have this variable here that is a churn risk that is affecting both our decision to send or not a promotion, because you can see that we are contacting a higher number of high-risk customers, and it's also affecting our the customer decision to churn or not. So causality helps in measuring the impact of our decision, overcoming bias. But we have also our second use case for today that is about targeting. And so which customers should I offer an anti-churn promotion to? So suppose you have a budget and you need to decide which customer to contact or not. And to do that, a lot of companies rely on predictive models. So anti-churn models that predict if a customer is going to churn or not. But obviously this is not enough, because this churn model is not really taking into account our decision to send or not a promotion. Indeed, you could have different conditions after your intervention. So looking just at people with a high probability of churn, you could have people that will still churn even after a promotion, and people that will not churn after a promotion. And so causality helps us in targeting the right customer based not just on prediction, because prediction and machine learning, traditional machine learning, does not take into account our intervention. And these estimations are done based on the potential effect. But how can we produce these causal estimates? We need some statistics, mathematics, but I know that today it's Friday, and the notation could be a little bit overwhelming with a lot of EV expected values. And so I'm trying to give you just a few takeaways from theory and statistics. And we need to first define two quantities here. The first is our treatment. In our case, it's just a binary treatment, so control 0 and 1 for treated. And we want to measure the effect of this treatment on the outcome variable. That could be retention, number of purchases. And with some hypotheses and some notation and statistics, you can reach an equation like that it's I really love this equation. So sorry, I need to explain this equation. And here we have three different terms. The first one is our observed association, and it's what we see in our data. In our Simpson paradox example, this would just be the difference between churn rates for contacted and not contacted. So it's what we measure in our data. This is equal to our causal effect. That is what we want to estimate here. It's the average treatment effect on the treated plus bias. So here we have two key takeaways. The first one is that observed association is equal to causal effect plus bias. So we can try to estimate our causal effect starting from observed association. But the second takeaway is that we need to deal with bias. And bias is something that we can try to understand. We have an equation here. And this equation tells us that the bias basically is the intrinsic difference between control and treated, supposing no treatment. So supposing that we are not sending a promotion, supposing no intervention. And this is just their intrinsic difference. Okay, so now we have to figure out how to do this estimation, and we have two main approaches to do that. The first one is experimental with randomized controlled trials, also known as A/B tests, with some more differences. And they're considered the golden standard for causal estimation, because here the treatment, our decision to send or not a promotion, is random. We choose these two groups randomly. And if you do that, as Pam from the office is telling us in this meme, these two terms that compose the bias would be the same picture, basically, because if you treat and treat with an equal probability, if you are choosing these two populations randomly, there is no reason why this intrinsic difference between our two groups should differ. But unfortunately, we can't always rely on these experimental frameworks, because we could have legal issues or ethical issues, but also we could have operational constraints like budget, timing, but also, for example, our boss is not really into statistics. So in these cases, we can rely just on our observational data. We should use just our observational data, but we know that our data is biased. We have this bias here. But bias is something that we can try to understand. And you can see here that we have two different forms of bias. The first one is a confounding bias. So we have a confounding variables here, the same that we have seen in the Simpson paradox example. And here we have our churn risk that is affecting both our decision to send or not a promotion and the retention. So the promotion is not given randomly. And this introduces bias because we are contacting, for example, more high-risk customers than low-risk customers. So we are introducing bias. To solve this, the trick was to group the statistics by the churn risk. So to control the churn risk, that means to compare customers with the same level of churn risk. So here the trick is to split the groups, but this is not always working because we could have a different situation. This is called a collider variable. And a collider is a variable like that, the purchase frequency, that is caused both by our promotion and the user retention. You can see that here promotion is not caused by other variables, and so you can assume that here the promotion is given randomly. So suppose the promotion is given randomly and not based on churn risk. Obviously, our decision to send a promotion can increase the purchase frequency of our customers, and also the retention can cause the purchase frequency to increase or decrease. For example, if a customer churn, the purchase frequency will be lower. So in this example, we have not bias in our data, but if you split your analysis by groups and you look at separated groups of churn frequency, so for example, just customers, if you look at the separated groups of purchase frequency, for example, high level of purchase frequency, you will introduce bias in this case. Because, for example, high customers with high purchase frequency would have a higher probability to have taken this promotion. So here we can't split our data by groups because we will introduce bias. But there are more systematical ways to deal with that. We have two frameworks. The first one is the potential outcome frameworks by Professor Rubin with a question like that. And the second one, that is a most recent approach, is a graphical approach with graphs like that. Here we have some tools to deal with bias starting from these graphs. They're called do calculus with the backdoor criteria and front door criteria by Jude Pearl, who is the author of the Book of Why, and he also won the Turing Award. But okay, for now, enough theory, enough equations, and let's try to see how it works in Python with a library. Here I'm using do-why, that is the most used Python library for causal estimation and causal machine learning, and it's part of the PyY ecosystem, and it was originally developed by Microsoft, but also other companies worked on that library. For this example, we actually need to collect some data, but unfortunately, when dealing with causal estimation, you do not really have ground truth in your data, because you can try to estimate causality, but you can't really measure causality in your observation. And so here I'm using a synthetic generated dataset, and this is quite common in research papers or online tutorials. And I'm generating a pandas data frame like that. We have our treatment, the churn risk, purchase frequency, retention. We want to measure the impact, the causal effect of treatment on retention. And I'm generating this data, and here I'm using this 0.3 treatment effect. That means that the treatment will increase the probability of retention of this quantity 0.3. Okay, now we can start try to estimate this quantity with do-why, and the first step, according to do-why, is causal modeling. Causal modeling means that we are not just using this data, but we need to model the causal relationships in our dataset. So how these variables are connected. And we see again from our previous slides that we have the churn risk that affect the treatment and the retention, and we have this purchase frequency here. And obviously here I'm generating this data, so I know the causal structure, but in real world application, this is really, really difficult. And to do that, you could rely on your domain knowledge, expert knowledge. You can do some try and error with experiments, but there are also some techniques, discovery algorithms that can give you the causal graph starting from graphs with some approximation. So this is really tough. But when we have our data and the causal graph, we have a next step according to do-why, that is identification. Identification means that we need to find out a strategy to deal with bias. And starting from this graph, do-why will try different strategies based on do calculus, based on the backdoor criteria, and this is a huge topic itself. But what the do-why is doing under the hood is analyzing this graph and provide us a strategy like that. And this equation means basically that to do causal estimate, measuring the treatment effect on retention, we should group this data by churn risk. So we should compare compare customers with the same level of churn risk. Okay, now we can finally make our causal estimation here. We are using the backdoor criteria, and we can use this estimate effect method from DoY. And here I'm using a linear regression, and you can see that we have pretty good estimation. But what's going under the hood is something like that. DoY is fitting a linear regression using retention as target and treatment and churn risk as variables, but not using the purchase frequency because it obviously would introduce bias. And basically, our treatment effect would be the coefficient of the linear regression, the treatment coefficient, and this would mean that we are trying to keep the churn risk constant when estimating this treatment effect on retention. Okay, we have one final step for our estimation, that is validating this estimation, because in our example, I've generated the data, so I know the causal effect, but in real world, you have not a ground truth for your data, and you need to validate your estimation. And to do that, DoY provides a suite of refutation tests that can be used to validate both your assumption, your causal assumption about the graph, your causal assumption about modeling. We are using a linear model here. It could be also nonlinear. And also the check for robustness for other hypotheses. Okay, now we know how to estimate the causal effect in our marketing campaigns, but we still have one problem, that is about targeting the right customers. Indeed, we could have heterogeneous effect in our campaigns. So we could have lost causes customers or persuadable customers, and consider this example. Here we are trying to offer a free beer coupon to Futurama characters. We have a group of treated and untreated, and we want to measure the causal effect on their retention. For example, you are a telco company and you provide a coupon for free beer or whatever you want. But as a Futurama fan, I really know that robots like beers more than humans. So I would expect a situation like that. I would expect the effect on retention higher than the effect on robots higher than the one for human. And we need a strategy to do that, obviously, automatically, starting from our causal assumption and our data. To do that, we need to define this quantity that is called conditional average treatment effect. And basically, it's a treatment effect looking just at X equal some subgroups in our data. For example, X equal is robot. And we can try to estimate that. This is called uplift modeling. And uplift models are something like that. We can try to estimate the uplift level, estimating the potential outcome supposing treatment and the potential outcome supposing no treatment. So trying to estimate, to predict the retention with treatment and without treatment. We have a really straightforward approach to do that is called S-learner. This is a meta-learner. That means that you can use whatever model you want. And here we have a training step. And in our training, we are fitting this model on our set of features. For example, is robot or is Planet Express employee. But we add also another variable here, the treatment. And the treatment would be 1 for treated units and 0 for untreated units. And we fit this model to predict retention. But at inference time, we apply this model 2 times. The first one supposing no treatment, the second one supposing treatment. And in this way, we can estimate both this outcome, supposing treatment and supposing not treatment, and we can estimate the uplift as the difference between these two quantities. And we can use this estimated uplift in order, for example, to sort our customers and to target just customers with a higher level of estimated uplift. Or you also can try to group these analysis by feature. For example, groups just to see the conditional average treatment effect on just robots or just Planet Express employees. But here again, we have some potential pitfalls, and we should be particularly careful about feature that we use or not in these models, because we have still to deal with our bias. We should avoid to introduce bias, and to do that, you should be particularly careful. Here we have some rules, but this is a huge topic. Okay, now let's see it in Python. Again, we have the same example that we have already seen, but now we have this isRobot flag that can affect the retention, because it's considered an effect modifier, because in case of treatment, the retention for robots will increase. And we can use the same step that we have used with the linear regression from DoY, but this time using a meta-learner, this S-learner from the library EconML. Indeed, you can integrate DoY with other libraries, or you can also implement your estimation method. And basically, you can see here that we are fitting a random forest. And then our model is used to predict the estimated uplift here. And here I'm trying to group by this result by this isRobot flag. And you can see that, again, we have good estimation in this case. Okay. Some final takeaways. We have seen a beginner-friendly introduction to causality. Today, there are a lot of topics that we have seen that should have a session to really discuss it. And I think there is huge room for improvement in this sector, especially from the Python community and the open source community, because there are libraries, but we can improve them. And also, my final takeaway is that causality is used in these prescriptive tasks, but it really helps you also in other kind of tasks, because it's a really training ground to start asking the right question on your data and not just implementing predictive model to solve business problems. Okay, thank you.
We have time for a few questions. Are there any raised hands? Go ahead there, or not really? So I just have a question. Is Zoidberg really a human?
Okay, yeah, I didn't mention it, but yeah, it was a joke.
Okay. Yeah. And I see a real question there with a hand raised.
Kidding.
Thank you for a very cool talk. I think causality is very interesting. You used some notation underway. So you had this like y subscript 0, y subscript 1, right? And you talked about the treatment effect and the bias you can introduce. But then later you drop those subscripts. So in particular, when talking about Kate. And I was wondering, well, what does the subscript actually denote? And do we also have this bias issue later in Kate?
Yeah. Here we have a lot of notation when dealing with that, because when you have a question like that, this term, it's meaning that you are trying to condition your analysis looking just at treated groups, and here looking just at untreated. And when you have this suffix here, this one, it means that you are trying to consider the potential outcome supposing treatment. But you can do it for treated and for untreated. So here it's done for treated. And here it's done for example, this is the potential outcome supposing no treatment for the untreated. And this is the potential outcome supposing not treatment for the treated. And so you can't observe that, and you can't really measure bias, but you can identify some strategies to deal with that.
And the second part, because later in the presentation you then drop these subscripts. Okay. So do you have here? Bias? Yeah, do you have this bias term also in K of X?
Because here you're looking, just at treated, and this is their outcome, and you are not supposing to treat or not. This is just the outcome in case of treatment. Yeah, maybe it's something going on with notation. I should check. Thanks for the advice.
Thank you.
Okay, thanks.
There was one other question. I think we can still have it.
So yeah, first of all, thank you for the very interesting talk. My question is more of maybe a general question. So you introduced your model, and then did you have, once the process was fulfilled, you kind of started getting labels, I assume. So were you able to actually kind of prove your kind of thesis here, and with that like the specific features were the ones most relevant? I mean, you could just basically, with the labels, do.
Yeah, I see your, thanks for this question. I see it's hard to test these kind of models. You can try back testing when you have real world data. You can try to do another experimental framework to do some A/B test to test on your actual collected data. But there are also these really nice refutation tests that you can use to validate your estimation, and they're based on statistics, and you can try to understand if this graph makes sense or not, and you can try to understand if your model makes sense or not. So you can test for validity of your assumption.
Yeah, I don't doubt your math. It was just to actually at the end see that the featers that you predicted are the most important. The interpretability, like if it kind of like aligned with that.
Okay, maybe
we're running out of time a bit, but we'll talk later. We can discuss it in break. Thank you very much.